Hi everyone, this is our fourth and final video for Chapter 8. I'm going to cover sections 13 and 14, which are looking at the topic of synthesis. We're going to look at just two sections in this video because it is getting to be a little bit more complicated of a topic, and we're looking at, in the first section here, how to predict products or reagents in a reaction. So just to make sure we have our language, reactants are drawn on the left-hand side, usually to the left of the arrow, and products are drawn to the right-hand side of the arrow. So those are terms we're familiar with, what we start with, what we end with. Reagents are usually drawn on the arrow and below the arrow. Now, generally, not all the time, but generally our reagents are drawn above the arrow, meaning what we're reacting our reactant with. And then under the arrow, solvent, some conditions, so maybe a temperature or a catalyst. Of course, there's exceptions to this, and sometimes we have lots of reagents and they go above and below the arrow, but this is just kind of a general formatting, so we make sure that we're all in the same language. So there's two examples here of how we might see this, and you can see the watermark back here. I definitely borrowed these from a website called Leah for Science. If you haven't visited her website, I highly recommend it. She has a lot of really good tutorials and a lot of good practice questions. So I just stole these for the visual, but I would definitely utilize her videos and her tutorials. I think that she presents her material in a great way. Okay. Onto the section. So what we're looking at is how to fill in these question marks, how to fill in these blank spaces, whether they are products or reagents that are missing. And there's three things that we're looking at. The first question says, what groups are being added to the double bond, or what groups were added to the double bond? So for example, for this first one here, we'd say, well, we're reacting it with chlorine and water. So we know the two things we would add to that double bond would be a chlorine and an alcohol. And then for this reaction down here, we compare what we started with to what we ended with. And the difference is that that center carbon gained a bromine and the end carbon gained a hydrogen. So we added a hydrogen and a bromine. And then the two other questions are the regiochemistry question, which is, was it a Markovnikov or anti-Markovnikov reaction? This one, we because it's chlorine and water, and we're adding to two carbons that are equally substituted, it's not a question we need to answer. Over here, our bromine added to the more substituted carbon, and so we know that that is the Markovnikov set of reagents that we need. And then the last question is about stereochemistry, syn or anti-addition. And so that's where we would include dashes or wedges into our products, or we would pick the syn or the anti set of reagents to give us what our product looks like. Now, between Chapter 7 and Chapter 8, we have quite a few reactions. And the instinct is going to be to memorize them, to make flashcards. And I'm going to push you in another direction. Memorizing them can be difficult. It might not seem like it right now, but as we add on more chapters and more reagents, the list becomes quite long. So a really good way to learn these is to look at their mechanisms, look at the patterns, kind of group them together. Definitely the first step of learning something is memorizing, but you want to move beyond that. You want to understand them and not just memorize them, because we want to be able to look at something like this and be able to figure out what that missing piece is. If you've only memorized reactant plus reagent gives us something, and you haven't thought about it from these other perspectives, then you might not be able to complete a question like this. So I'm just kind of giving you a little word of warning on making sure that you are going beyond the memorizing. So here's our practice problems for this. We're going to look at 3 separate reactions and use that technique of the 3 questions we're asking ourselves to figure out what we're going to reveal from these boxes. So in our first set of reagents here, we have KMnO4 hydroxide, and it's under cold conditions. So the first question was, what are we going to add? We know that this set of reagents adds 2 hydroxides or 2 alcohols to our alkene. If we look at our reactant here, it looks like there's a lot of alkenes, but there's a difference. On the left-hand side here is a benzene ring. Benzenes are highly stable. So the types of reactions we learned in Chapter 8 do not affect a benzene ring. So the only alkene that will react is going to be this one right here. Regiochemistry, it's not really a concern because both carbons are getting an alcohol. So we don't have to say which carbon gets what because they're getting the same thing. Stereochemistry, we know that it's going to add in a syn addition. So we can draw this with both alcohols as a wedge or both alcohols as a dash. So here's our final product, and we don't even need to put plus an enantiomer on this one because it is a meso compound, our plane of symmetry right here, and so we just get this one final product. All right, in our next one, we have our alkene on a ring. We're going to react it with borane in tetrahydrofuran and hydrogen peroxide with sodium hydroxide, and we know that this is a hydration reaction. One of these carbons will get a hydrogen and the other one will get an alcohol. So to answer the regiochemistry question, this is an anti-Markovnikov reaction. So we know that our alcohol will go to that less substituted position. And it is a syn addition. So our hydrogen and our alcohol will both either be wedges or dashes. So here is our final product, and I'm going to draw in that missing hydrogen right here. So our hydrogen would be on a dash right there. And it does say plus an enantiomer, so we would get our other structure where the hydrogen and alcohol would be on wedges and that methyl would be on a dash. And then our last one here, we have a structure with 2 alkenes. It's not a benzene ring, just 2 alkenes in the same structure, and we're reacting it with hydrogen and palladium. So we know that what we're adding, 2 hydrogens. Again, we don't need to answer that regiochemistry question because each carbon's getting a hydrogen. And our stereochemistry question is that it's going to be a syn addition. So they're both going to be wedges or both going to be dashes. So we do end up with 2 different structures here because when we add in our hydrogens, I can have both of my hydrogens on each of my double bonds as dashes, which would be our first structure here. Finish my dashes. There we go. Or on the second structure, we could have one side as dashes and one side as wedges. So the 2 hydrogens that are getting added have to be syn to each other. So meaning these are syn to each other and these are syn to each other, but they don't have to be syn all the way across. So we get 2 different stereoisomers of each other, and these would be diastereomers. So what about the other part? What if we're trying to figure out what our missing reagent is? Again, we're going to ask the same question. So if we compare our reactant to our product, what we see in the difference is that we look at this alkene position here, these 2 two vinylic carbons. The more substituted one gets an OH group, and the less substituted one gets a bromine. So it tells us the 2 things that were added, and it tells us their regiochemistry. We aren't given information about the stereochemistry. We do see the alcohol on a wedge here, But because there's two hydrogens on this bromine, we're not given information about the bromine's stereochemistry because this isn't a stereocenter. But we know that in order to add a bromine and an alcohol at the same time, we can use Br2 and water, and that will give us our final product here. In the next structure, on our alkene carbon, we compare our starting material or our reactant to our final product here, and we've added a hydrogen to this carbon, and we've added a bromine to this carbon. And again, we have some stereochemistry over here, but we're not given any over here. We do have regiochemistry though. We know that our bromine was added to that more substituted side, so we know that it's a Markovnikov product. So that means that it will be HBr. And then in our last one here, it looks quite a bit different than the other ones. Over here we have 1, 2, 3, 4, 5, 6 carbons with a double bond in between them, and over here we only have 3 carbons with now a carbon-oxygen double bond. But we do know one reaction that would make a carbon-oxygen double bond, and it would essentially cut this structure in half, giving us 2 3-carbon structures that would be identical. So if we use our ozonolysis reaction, we would get these 2 ketones, and really this is times 2. There would be 2 of these for every one of those reactants that would react. So in this next and last section of this chapter, we're putting together all of the reactions we've learned so far. So chapter 7 and chapter 8. And this slide is giving us essentially a reminder of what we've learned so far, how we can group our reactions. Chapter 7 looked at substitution, so taking one leaving group and replacing it with a nucleophile, and elimination, taking away a leaving group and a beta hydrogen and replacing them with a double bond. So this is chapter 7. I know it's obviously a lot more complicated than that, but this is the big idea. Step back and see what it's really teaching us. This is the big idea. The top reaction is chapter 8. We're starting with an alkene and we're adding something to each of the vanillic carbons. So all of the reactions we've learned so far can be summed up into one of these 3 categories. We're going to talk about 2 different strategies on these multi-step synthesis. So a multi-step synthesis is going from one structure to another, and it will require a few steps, multi-step. And so we're looking at a couple different strategies on how to approach these problems, or even how to make certain carbons reactive. And what I mean by that is if we look at this structure, we know how to react a carbon that has a leaving group on it, but we don't know how to react any of these other carbons. So we can make these other carbons reactive though by moving the position of the leaving group. So in this first reaction here, if we want our leaving group to be over here so that we can add an alcohol there or put a sulfur there, whatever it might be, we need to move that leaving group. And we can do that through 2 back-to-back reactions. So the first reaction is to do an elimination. And notice we want the double bond on this side. We don't want the double bond to go over here. So because of that, we're going to not use the tert butoxide. Our tert butoxide would have our double bond giving us the Hoffman product, and so we don't want to use a bulky base. Instead, we want to use something smaller like a methoxide group. Our methoxide group would give us that Zaitsev product, which is what we're looking for. And then in the second step here, we want our bromine to go onto the more substituted carbon using our Markovnikov rules, and so we can use HBr for this. If we use HBr with peroxide, the bromine would go right back to where it was originally. So using those rules, using the base size to our advantage, we can manipulate where different groups will appear. The bottom one down here is moving the alcohol from this carbon down to this end carbon. Now in this one, we do want our elimination to give us the Hofmann product. We want it to go to the less substituted position, but first, we have to make our alcohol into a better leaving group. So we're going to use tosyl chloride with pyridine, followed by our tert butoxide. So remember, our alcohol is not a good leaving group, so we had a section on how to make it into a better leaving group in our last chapter. And then we have our tert butoxide, which will give us our Hofmann product with our less substituted alkene. And then down here, we want that alcohol to be on the less substituted carbon, so we would want to have the anti-Markovnikov addition. So we're going to use our borane set of reagents. If we just added acid and water, our alcohol would go right back to where it was. So it's really important to have more than one set of reagents that do similar things, like our OME and our tert butoxide. They do a similar job, but in different ways. The second strategy we're looking at is moving a double bond. And so in this example, we have a double bond right here in pretty much the middle of our structure, but if we want that double bond to be on the end, then we can use some of our reagents that we've had to do that. Just to add some language to this, this is called an internal double bond, which makes sense. It's in the middle of the structure. And then this one is called a terminal double bond. I think I've used that word before, but haven't properly defined it for us. So they're just words to describe where a double bond is located. So the first step here is replacing this double bond with our bromine, because we know bromine's a good leaving group, and so essentially we're saying, well, if we have a leaving group in this position, then we can use this side over here, we can use this beta carbon and beta hydrogen to do our elimination. In order to do that addition, though, bromine needs to go to that less substituted carbon, so we need to use our HBr with our peroxide, because that will be our anti-Markovnikov addition in order to get that bromine right here. And then, when we do our elimination, we want it to go to that less substituted side. We want to get that Hofmann product, so we're going to use our big bulky base, our tert butoxide, to force our double bond into that less substituted position. All right, we're going to put all of this information together and do two big practice problems, and I'm going to approach them from two different perspectives. We're going to do the first one in a forward direction, and then we're going to do the second one backwards, which sounds kind of weird, but I'll explain it on the next slide. So here's our question. It says, propose a multi-step synthesis for the following transformation. So we have two structures here. We have our reactant, we have our product. The first thing I like to do is to take inventory. We look at what is in each compound. So we have 5 carbons, and there's a bromine on carbon number 2. Over here, we have 4 carbons and an aldehyde. So this tells us that our functional group has definitely changed. We go from a halogen to an aldehyde, and we're losing a carbon along the way. So we have to think about what we have in our reaction toolbox and how we can go from this structure to this structure, knowing that it will take a couple steps. We want to be able to create this carbonyl, and we know we can do that if we have a double bond. So going that route might be our best bet. So our first set of reagents then would be to use our tert butoxide, so we get that Hofmann elimination product with our double bond over here. Now, as you're doing these and practicing these, you might not know what pathway to go down when you first start them. And you might end up with a pathway that doesn't quite work and doesn't quite make sense on your first try, and that's okay. You just erase it or cross it out or turn your paper over and start over. we are learning these tools, and so you're not going to master them immediately. Also, there's more than one right way to do most of these. So I'm showing you a very short pathway. It's only going to have 2 steps. But if you work on this by yourself, you might have come up with a pathway with 4 or 5 steps. They both could be right. Now in reality, when you're doing this in a lab setting, we would want the most efficient pathway, which means that it would have the least amount of steps, because you guys have done enough labs that you know that every time you transfer your product, you lose some of it. It sticks to the glassware, it sticks to your stir rod. So we would want to have the least amount of steps. That also means it's less time and less money. But if we're just doing what I like to call paper chemistry, then it doesn't matter. We just want to find pathways to get from reactant to product. All right, enough of my side road there. All right, so we've created this alkene. It still has 5 carbons, but it now has this double bond, and we know that we can cut that double bond in half to give us our aldehyde at what would have been carbon number 2. So essentially we're cutting off carbon number 1. And we can do that with our ozonolysis reaction. So this turns out to be a 2-step reaction: elimination followed by ozonolysis. Now we can put them in a little stepwise like this, or we can put them all on the arrow showing us how we would add our reagent. So our elimination followed by our ozonolysis followed by that dimethyl sulfide workup in our ozonolysis step. All right, here is our last one that we're going to look at. Same instructions, which means same typo. But here's what we're going to look at. We have a cyclohexane with an alcohol attached, so a 6-carbon ring with an OH group, and we want to make a 6-carbon ring with a sulfur methyl group attached. So the ring part isn't changing at all, which is good, but we need to swap out that alcohol for this sulfur group. We know that alcohols are bad leaving groups. We know that sulfurs are good at being nucleophiles. So we're going to use that to our advantage. And I did say we're going to approach this one from a backwards perspective. So this is technically called a retrosynthesis. So instead of taking this and saying, how can we get to our sulfur? Instead, I'm going to say, well, I know that I can add a sulfur to this ring if I have a good leaving group on there. So if there was a bromine there, I know that I could react this with NaSCH3, and I would go through a substitution reaction to get that sulfur on there. And I know that I can get that bromine on there if I have a double bond, because I know that with a double bond, I can react it with HBr, and I'll add a hydrogen and a bromine to those 2 alkene carbons, and I will have the right intermediate. And then looking at where we're at, we know how to go from an alcohol to an alkene in a couple different pathways. Probably the most straightforward, though, is using concentrated sulfuric acid. And concentrated sulfuric acid will give us that direct elimination. So taking a backwards perspective is called a retrosynthesis. It's often common for us to kind of combine the two, working a little bit forwards, a little bit backwards, to try and meet somewhere in the middle. Both approaches work. I'm not going to force you to take one approach over the other. So use those tools that we've learned in these last couple chapters as you are practicing these types of questions. All right, that is it for our chapter 8. Thank you.